Hello, everyone. On behalf of Hailey Wang of the NOAA National Weather Service Climate Prediction Center and Viva DeHeza of the NOAA Research's National Integrated Drought Information System, I'm Andy Hoyle of the NOAA Research's Physical Sciences Laboratory, and we welcome you to the inaugural NOAA Drought Seminar Series. The NOAA Drought Seminar Series is a recurring monthly event dedicated to drought monitoring, prediction, and predictability. The seminar's primary objective is to establish a focused platform where national drought research, operational, and user communities can exchange the latest tools, research findings, and risk reduction activities. This series aims to enhance NOAA's capability to monitor, predict, and understand drought behavior. Drought is a key focus area of the National Weather Service operational forecast products and services, supporting stakeholder decision-making and reducing drought-related costs and impacts. Drought is also a key part of NOAA Research's science priorities, aimed at confronting the challenges of a changing planet. Drought ranks among the most costly natural disasters impacting the United States, surpassed only by tropical cyclones and strong storms. Each seminar will feature a speaker presentation, a question and answer period with the presenter, and general updates on activities within the drought science and services community. Introductory remarks will be delivered by Wasila Chiao, Deputy Director of the NOAA National Weather Service Climate Prediction Center, and Roger Puardi, Senior Scientist and Acting Director of the NOAA Research's Physical Sciences Laboratory. Wasila, please start us off.
Yes, thank you. Thank you, Andy, for that introduction. Thank you to Highland and Viva for inviting me to say a few words during this inaugural seminar. I commend you for this cross-NOAA collaboration within NOAA to advance the dialogue in transitioning drought science into operation and possibly actions to benefit society. I'm honored to represent CPC as our director, David Novak, is traveling this week. But I'm also here to represent the National Weather Service, as I am the POC for ongoing U.S. Drought Monitor conversation within NOAA to make the U.S. Drought Monitor better and more accessible. I'm really glad to see that Viva DeHeza, Executive Director of NIDIS, has joined the organizing committee. You have a great program aligned, and I look forward to seeing as many of the presentations as possible. The seminar series could not be timelier as we witness unprecedented drought here in the United States. We are already seeing water shortage and wildfire in the West due to record snow, drought, and extreme heat. The mission of the Climate Prediction Center is to provide real-time updates of the state of the climate system and forecasts. The U.S. Drought Monitor's most recent update indicate exceptional drought in northeastern Colorado, drought that happened only once or twice in 100 years. And we're hearing that snowpack is just about 20% of normal. This clearly is a major threat to critical water supplies, causes low reservoir levels, and increases wildfire risk. Colorado is just one of the worst states in the West, but much of the intermountain region is affected. And we see the same pattern in the southeast as well. The problem is that we're not expecting much relief anytime soon. We have released our ENSO Outlook update last week, indicating an El Nino watch, suggesting a high probability for El Nino to develop over the next 6 months. We are predicting more than 85% chance for at least a moderate event by the fall of 2026. We know this has implications in the northern tier of the country, which tend to be dry during El Nino. Our seasonal temperature and precipitation outlooks favor above average temperatures and below average rainfall across much of the West during the spring season. It's not only about precipitation temperature, but also soil moisture, runoff. So our seasonal drought outlook for the spring, which takes into account a comprehensive list of variables that influence drought, suggests that drought will persist through the early part of the summer. So we are doing our best to monitor, predict, and disseminate the information real time. We are incorporating the best science available to us And I would like to take this opportunity to acknowledge the historical advances in drought science over the past decade to improve our understanding of drought and our predictability and our capability to monitor and predict. I can say that despite known issues, the US Drought Monitor is overall a much better improved product today than it was 10 or 15 years ago. Drought is a complex issue as it is multidisciplinary and touches upon various stakeholders, and drought perception and decision to be made can vary across the stakeholder spectrum. So beyond advancing the science, we have a lot more work to do to make our drought information more accessible and actionable. How do we bring in partner agencies within National Weather Service, the Water Center, for instance, and outside of NOAA, USDA, USGS, the Army Corps of Engineers to work collaboratively on this complex problem for tangible, on-the-ground action to mitigate societal impacts of drought? And this is where I'm going to turn it over to my good friend, Roger, Acting Director of PSL, for further insight into drought science and actions. Thank you.
Okay, great. Thank you, Wasilla. So yeah, I'm Roger Polwarty. I wanted to mention a couple of things, just following on Wasilla. I'm the acting director of the Physical Sciences Lab, which focuses on water-related extremes and water availability. And we've been engaged, and relative to the importance of this webinar, in what we're calling, the grand challenges for linking disaster risk reduction and long-term global change. And if, as Kelly Redmond, a legendary climatologist and climate services provider, said years ago, if you don't get drought right, you're not getting adaptation right. And this is why I think this seminar and webinar is actually critical across the board. As Wasilla said, there's a lot of cross-agency interest, there's a lot of cross-partner interests. And he mentioned all of those within the US on which we work. I'll mention a couple other things. The UN Convention to Combat Desertification produced a global drought atlas that we were engaged in, and that's an ongoing product. And of course, as he pointed out, you're seeing the driest years on record in terms of January in the Southwest, long-term drought conditions in Europe since late March 2026, dry conditions over large parts of Brazil, Argentina, and Chile, showing the importance of understanding the Earth's system and its predictability, but also how that information gets used to help us think through issues like water and energy, agriculture, and food security. Now, we know what we ought to do, but we know what we ought to do if the system is not, in fact, changing. Stronger early warning systems, nature-based solutions, resilient infrastructure, and cooperation across the globe are things that we've advocated for a long time. But the nature of the risk is changing over time. And that's whether it's anthropogenic, it's not that alone, it's the combination of variability, change, the exacerbation of extremes on a slowly varying background. That's what we're here for, to really understand whether or not we know what the problem is. I like to tell people, confidence is that nice warm feeling you have when you don't understand the problem as yet. And so as we go through this, and the seminar and the webinar series, as pointed out by Wasilla and others, we'll hear a lot of terms in terms of thinking about drought, the cumulative impacts, the drivers from the standpoint of soil moisture, circulation, the issues surrounding trends in river flow, groundwater levels, and so on. Critically, the question is one of non-stationarity. It's a question of exposure, compound and cascading hazards, and very importantly, how we model and assimilate data from very complex environmental data sets. Most importantly, it's the regional and local specificity. And this is where NIDIS, National Drought Mitigation Center, and others come to bear in thinking through how we quantify these complex interactions. Those are driving international partnerships, they're driving national ones, they're driving regional ones, and we hear this constantly from the Western governors, the Mississippi River mayors, and others on trying to get around this question of drought. We didn't wake up yesterday and thought, wow, drought, we're not doing that. But we have, as the first speaker, and you'll hear more about him in a second, someone who has the credibility to tell you, I told you so. That's pretty important for a scientist. And the question is, how do we ensure that we're using what we know to help reduce risk and create secure environment. So drought research and applications are increasingly focused on interdisciplinary approaches spanning weather, water, climate, ecology, and varieties of social science to manage risk and build resilience. Those connections are what brings us here. Most critically, it is realizing the public benefit of scientific research, and by science I mean physical, social, and decision making, and how they lead us to reduce risk and create more resilient societies. This has been the goal for many of the programs you heard from Wasilla, for what you will hear in the future. And I wanted to keep that in mind as we go on as the backdrop to thinking about the pathways into the future, how we shape that, much beyond things like co-production, into how we co-develop a future with better science and information. And we have no better person to start that off with to give us a sense of the pathways and what's happening in the background Earth system. So thank you, Andy. Thanks to the whole team for putting this on. There's salience around the globe, as shown by the people who have signed on and the people that we've all have sort of entrained into this process. And it's very clear that we need to understand past events very well and whether or not we actually learned the lessons from those and not just drawn them. Thanks, Andy.
Thank you very much, Roger. Thank you, Wasilla, for your remarks and your insights. Please note that this seminar is being recorded and will be uploaded to the seminar homepage in the next few days. Attendees are welcome to submit questions using the question and answer feature at any time during the seminar. Questions will be addressed after the speaker has concluded. The method for accessing the question and answer feature in WebEx varies depending on whether you're using the browser or the application. Nonetheless, you can find this feature in the lower right-hand corner of your screen. For those using the application, the Q&A feature is called Slido. Feedback on the NOAA Drought Seminar Series is most welcome. Please use the email in this slide with comments or suggestions. And finally, future seminar information, recordings, and email sign-up are available at the seminar webpage found on this slide. Today's speaker is Richard Seager. Richard is the Ewing Lamont Research Professor at the Lamont-Doherty Earth Observatory of Columbia University in Palisades, New York. After undergraduate studies in England, he earned his PhD at Columbia in 1990. Then, after a postdoc at the University of Washington, he returned to Lamont for good. His work studies ocean-atmosphere coupling and its connection to the global hydrological cycle on timescales of weeks to millennia. Richard is a fellow of the American Meteorological Society and the American Geophysical Union. He was the 2024 recipient of the American Meteorological Society Charney Medal. Richard will now present Pathways of Ongoing Aridification in Southwest North America, Linkages Across Seasons in the Ocean Atmosphere Land System. Richard, please take it away, and we're delighted to have you today.
All right, thanks, Andy, Wasilla, and Roger, and very happy to be here speaking about this important work with so many people. So I'm going to share my screen. We've tried all this before, so it should work. And let me play. Do you all see that?
Yes, we see your slides.
Great. Okay, so we have the title, and this is work that we've been doing at Lamont-Doherty Earth Observatory over the past several years. And critically, we were funded by NOAA to do this, but this has also been a very large project, and we've also been enjoying funding from NSF and until recently, Department of Energy as well. And the talk has sort of a large part of it is it's about drought, and then a little bit of it is also about the tropical Pacific Ocean. And you can see the team members I've been working with on those different aspects of this. So as already alluded to, this is the drought monitor map that was released last Thursday, valid last Tuesday, and it's been like this for a few weeks now, but it's really an absolutely remarkable situation where most of the United States is now in some level of dryness or drought, including where I am up in New York. We had a very snowy winter, but the snow is all gone now. And I was up in the hills north of New York City just yesterday, and it's remarkable how dry the soils are up there now. But of course, it's much more intense out in the west and also right now in the southeast. The rest of my talk is going to be talking about the southwest, and I just plotted here on the right the century-long records of precipitation and temperature from gauge data for a big area of the southwest. And you can see like the run of dry years that we've been having in the west. Quite a lot of dry years since about the turn of the century, but probably no absolute long-term trend there on the 120-year timescale. But then temperature has just been climbing and climbing and climbing. And this is some work that was led by Ben Cook last year, where it's a classic combination of instrumental records for the modern period with tree ring reconstructions, which in the West go back to the year 800. And you can see there at the top left in just the plotting of the raw data, this extensive period of dry that's so far proliferated in the West, in the Southwest in the 21st century, which clearly is looking record breaking. And then the blow up of that for 1900 to now. And what's remarkable in the last half century or so is this swing from a very, very wet period in the late 20th century to this extended dry period, which we're calling a megadrought, that has so far prevailed in the 21st century. And you can see in the bottom right that that really is being led extensively by the change in the precipitation. And in this paper, Ben looked at all the extended pluvials and all the extended droughts, 5 years or more, and made these box and whisker diagrams of them, and then plotted where the 21st century megadrought and the late 20th century pluvial, and then this earlier 20th century pluvial, that was the long period of wet conditions that preceded the development of the sharing of the Colorado River, ironically. Those were two extremely wet periods in the last millennium, but this most recent late 20th century pluvial, by some measures, is the wettest, is the most extended wet period that has occurred in this millennia-long record. But this swing from that very wet conditions to these very dry conditions is quite remarkable. Referring again to some work that was led by Park Williams, who used to be here but is now at UCLA. They looked at this current mega drought and again looked at it in the context of tree ring reconstructions going back to 800. And these are reconstructions of the top 2 meters of soil. You can see where the 2021 anomaly is there. It's one of the handful of driest extended periods in this very, very long record. And the way that this reconstruction is done, you can remove the influence of long-term trends, like an anthropogenic warming trend. There's very little anthropogenic precipitation trend, according to CMIP6 models in this region. So the main impact has been the warming. And when you do that, you can, and if you remove it, you can reevaluate what would have happened without the anthropogenic impact, and then assess how the current megadrought ranks against all the prior ones. Right now, with the full record, it appears often in the top 5 ranked megadroughts that has ever occurred in over 1,000 years. In some places, it's the most severe. But if you remove that anthropogenic climate change from that modeling exercise, it's a much more mundane megadrought. You still have a megadrought, but it's not going to be wouldn't have been as severe as it is without the influence of the anthropogenic climate change, which in this calculation is primarily coming about from the warming. But we saw that in that transition from the late 20th century into the early 21st century, it was really the being driven by this drop in precipitation. So now I'm going to shift gears and talk about what it is that's driving the precipitation decline during this ongoing southwestern megadrought. So to look at that, we're going to use some NOAA precipitation products, the ERA5 reanalysis, and we're going to be running a version of the CAM6, which is the NCAR atmosphere model. And it's a version that we set up to run faster at Lamont. It has a bit lower resolution. We removed the chemistry. And for the historical period forced by observed sea surface temperature, we have 16 ensemble members. So this is running through with the observed history of monthly SST over many decades underneath it, and we're going to see if it can produce the observed change in precipitation. And we find that in its ensemble mean, it does reproduce this remarkably well. So the middle picture there on the left is what we get from atmospheric reanalysis from ERA5. It's the precipitation in colors and 200 millibar geopotential heights. And there's a very classic La Nina-like pattern of heights with a high, a low, and a high over North America. The sea surface temperature change between the 21st century and the 20th century is in the top up there, and you can see the cooling that has occurred over the equatorial Pacific Ocean during that. And that's an actual cooling. That's not relative or anything. It's actually got colder there, and that's a major swing in the Pacific decadal oscillation. In the middle on the right, you've got the atmosphere model, which is able to reproduce this teleconnection pattern rather well. It's clearly coming in a wave train from the equatorial Pacific Ocean. So it's the tropical Pacific sea surface temperature history that is driving this decline in precipitation. The time series with colors on it in the bottom row shows a comparison of the cool season precipitation between observations and the atmosphere model. And that's got a correlation of about 0.66. So a significant share of the history of precipitation is being dictated by the sea surface temperatures. And then in the precipitation is shown in box and whiskers here for the late 20th century and then for the early 21st century, and that's the distribution across the 16 ensemble members, and they don't even overlap. I mean, this was such a significant SST force regime change that the precipitation distribution in the 21st century has been significantly drier and separated from the distribution in the end of the 20th century. Observations show that there was actually a summer reduction in precipitation too, but our model does not get that. And that's consistent with the oceans having a much stronger driving of the atmosphere and precipitation over North America in the cool season than in the warm season. In the spring, soil moisture in the model, in the atmosphere model, also tracks that in observations, correlation coefficient of about 0.7 there. And again, you can see how separated out the distribution of soil moisture in spring is between the two periods, and again with the model reproducing the observations. And this is in actual units. There's no standardization here. This is actual units of water in the soil. And that spring drying is coming about from this cool season reduction in precipitation. But often when we're talking about drought, we like to think about the summer soil moisture, which is the growing season. And sure enough, the model is able to reproduce in actual units the change in summer soil moisture between the late 21st century and the current ongoing 21st century megadrought, as well as the time history of the summer. Now, remembering that the model did not reproduce the summer drop in precipitation, this is a soil moisture drying that is inherited from the cool season reduction in precipitation. And that's very key here, that we're seeing summer soil moisture is really tracking the cool season precipitation. And that's seen here where we're plotting this difference across all the ensemble members, and the observations are the one down at the very bottom left there. And you see that the ensemble members have different realizations of internal atmospheric variability in them, so they create a distribution. But the amount of soil moisture drop that occurs in the summer is well correlated with the precipitation difference in the prior cool season. And the linear relationship between these seems to track between 0, 0. So we don't seem to see any evidence in this record of an additional soil moisture drying from temperature increase. Instead, this difference is being controlled by the cool season precipitation difference. Okay, so shifting gears now to the tropical Pacific Ocean, we just found, I just showed you and hope convinced you that the precipitation in the cool season in the southwestern United States is very much influenced by the sea surface temperatures in the tropical Pacific Ocean. And it went through that big PDO swing around about the turn of the century. But when we look on longer time scales, here going back to 1958, which is when the ECMWF ocean reanalysis begins, that was what dictated the start period here. When we go back looking over that period, we see there's a significant difference between the pattern of sea surface temperature change in the tropical Pacific Ocean on the top left, which shows a region along the equator where there's been actual cooling of water, and a wider region or a more longitudinally extended region where there has been essentially no warming, versus what CMIP6 models say should be happening in response to increasing radiative forcing, which is actually an enhanced warming in that area. And this has been a known discrepancy in models going back a couple of decades now, and it's still disputed, but we, at least in our group, we feel very strongly that this observed cooling trend in the equatorial Pacific Ocean is a forced response, and that the models are actually getting the forced response wrong. Interesting when you look below the surface of the ocean and in the lower two panels here, which is a depth longitude cross section along the equator, you see subsurface cooling below. In the real world, it's very strong, and it's a combination of enhanced Ekman upwelling and reduced vertical mixing of heat down that is causing that, and we've shown that all in those papers listed in the bottom right there. But you also see that in the real world, this is connecting up to the surface, that this enhanced stratification with cooling below is being mixed up and upwelled and helping cool the equatorial surface waters. Whereas in the models, they do have a muted subsurface cooling, but the models stratify over such that this is kept isolated while the surface warms. And we're now thinking in the group here that these vertical processes that mix and move heat in the vertical in the equatorial ocean are being misrepresented in the models, so that they're getting this incorrect response to the rising radiative forcing. From what I've talked about so far, that should actually matter significantly for the sea surf, for the climate in Southwest North America. But first of all, to sort of emphasize this point about the difference between the models and observations, this is from a paper just recently published by one of my PhD students, Hannah Byrne. And what she did here was compute trends across all possible start and end dates of longer than 20 years. And the color in the triangle picture shows whether the east-west gradient has been strengthening, purple, or weakening, green, for every single possible start and end date. And if it's hatched, it means it's contained with a trend of that strength is contained somewhere within 14 CMIP6 large ensemble models. So that adds up to several hundred individual model runs. And you can see that for trends ending in the 2000s, especially in the last decade, regardless of when it is that they start, those are largely outside the range of this enormous collection of runs with CMIP6 models. And this actually uses 5 different observational data sets and statistically is weighting them. So this is like outside the range of observations. So this is a major model discrepancy. Now, I want to make clear that what we're talking about here in terms of the forced change is distinct from the pattern of natural decadal variability. So I've mentioned the specific decadal oscillation, and when you look at trends over 1980 to 2022 or something, a period like that with 2000 in the middle, the PDO went through this transition around about the end of the 20th century, sort of after the 97, 98 El Nino. So that 40-year trend, which is common because it coincides with the beginning of the satellite era, that 40-year trend is really very strongly influenced by the trend in the PDO. And if we take that trend and then we compute all possible 43-year trends before and run a pattern correlation between those trends and the 1980 to 2022 trend, then we end up with the picture at the top here on the right, and we see that this pattern has oscillated back and forth over time, right? So this pattern has appeared in its opposite form, trending over the middle of the 20th century when the PDO went through an opposite phase transition. And it's done a phase transition like this recent one before, earlier in the 20th century. But if we take this very long-term trend, this 1958 to 2022, and do the same exercise with that, we take that trend, we compute 64-year trends stepping back in time and compute the pattern correlation of those trends with the most recent one, we find that this is a pattern that has actually been emerging over time. It hasn't oscillated back and forth. It's just steadily emerging over time. And this is work that was being led by my postdoc Feng Zhang in a series of papers. So please be aware that there are more than one thing going on in the tropical Pacific Ocean. And the way I think about it is there is this natural decadal variability going on. But on top of that, and consistently emerging and strengthening over time, there is this Pacific climate change pattern. And it has this, amidst general tropical Pacific warming, it has this region of equatorial cooling along the surface, which we think is related to these vertical processes in the ocean. So we need to look at this, what the implications are. And multiple SST data sets, you find this same emerging pattern. So let's model now the implications of this for the Southwest. So the modeling exercise that we did here, and this was funded by NOAA just a few years ago, we generated this anticipatory assessment ensemble, which is a unique large boundary value ensemble. So the point here is that this is an ensemble of atmosphere model simulations forced by sea surface temperatures. So we don't think that the CMIP6 models correctly simulate the Pacific Decadal Oscillation or the AMO, the Atlantic Multidecadal Oscillation. So instead, what we're going to do is create scenarios of PDO, AMO, and ENSO variability using a linear inverse model trained on historical SSTs. So that ensures that the patterns that the model will see are the ones that have the same physical character in both space and time as the ones that are observed. And then we run a series of ensembles with different combinations. So they have PDO and AMO are varying realistically, but we've selected ones that have overwhelmingly PDO positive, AMO positive, the PDO negative, AMO positive, and so on. And then for each of those combinations, we have 16, and they have different ENSOs within them too. So that's why this is not an initial value ensemble. This is a boundary value ensemble. So that's the way that the SST variability is represented. Now, we also need to impose upon it the change in SST due to the response to radiative forcing. And we do that in two different ways. One is we just take it directly from the CMIP6 multi-model mean, and that's the one that has the equatorial Pacific cold tongue warming up. And then the other one is we extrapolate the observed SST record using regression on greenhouse gases. We then take the same CMIP6 greenhouse gases for the future and the same regression coefficients, and we project forward. And that will continue the observed pattern where we have warming in almost everywhere, but we have that cold tongue cooling along the surface. So it extrapolates out into the future. And then with these, we combine the variability and the forced SST to create realistic SST scenarios, 2 ensembles, one CMIP6 forced response, one extrapolated observed forced response, and then we run them out to 2040. And this ensemble will contain with it many feasible states of decadal variability plus forcing. So the PDO negative and the AMO positive, that means a cold tropical Pacific Ocean and a warm tropical North Atlantic Ocean is the worst case scenario for the Southwest. And I'm plotting here the precipitation in color and 200 millibar height anomalies in contours, and by season for winter, spring, summer, and fall. So you see in winter and spring, we have this high-low high pattern over North America, and it's a nice ridge in the spring, and you see the reduction of precipitation. Because this is a cool Pacific, warm North Atlantic, we see the reduced precipitation over the equatorial Pacific and increased precipitation over the tropical North Atlantic, and a characteristic wave train coming from that is placing dry conditions over Southwest North America. This goes back to the very first NOAA Drought Task Force from almost 20 years ago now. I think it probably was 20 years ago now, where Siegfried Schubert led that. And this was like the perfect ocean for North American drought when the tropical Atlantic is warm and the tropical Pacific is cold. So that's this worst case scenario that exists within our large ensemble. If we average over all the different PDO AMO states that we ran, then we isolate the role purely of radiative forcing, and we see that that alone is also creates a ridge over the North Pacific and is drying over Southwest North America. So that's the response to the pattern of SST change, and the illustration here is for the case where we're extrapolating the observed sea surface temperature trend forward. So here I'm plotting the same worst case and then the radiatively forced case, but now it's 700 millibar heights in contour. The sea surface temperature is plotted over the ocean in color, and soil moisture is plotted over the continents in color as well. And you see in that worst case scenario that we have dry soils across Southwest North America throughout the year, driest in the spring, and you can see the cool waters in the tropical Pacific Ocean there, especially in the winter season. In the forced response, and this again is with the Hadley observed SST extrapolated forward, you still have that cool there in the equatorial Pacific Ocean, but the forced response also gives a winter-spring ridge over the North Pacific. And again, even without, after averaging across all the possible PDO AMO states, we're getting this reduction in soil moisture. Not as serious as in the worst case, but this forced response is also a drying. So what is the impact of the difference in the SST projections? So here we have the cool season precipitation and 200 millibar height anomalies. On the left is the case where we're using the observed record and extrapolating it forward to 2041. We have the ridge over the North Pacific and the drying soils over North America. The one where we use the CMIP6 SST, which warms up the equatorial Pacific Ocean, is the middle case. And in this case, we have a much weaker ridge over the North Pacific. And consistent with that, much less drying of soils over the Southwest, although they still do dry a little bit. And then the difference, which is due to these different possible SST futures, is the one on the right. If the sea surface temperature trends in the tropical Pacific continue the way they are without the equatorial Pacific warming up, then we get reduction in precipitation along the equatorial Pacific, low geopotential heights above there, and a wave train coming from there with a ridge over North America, and consistently a reduction in soil moisture over Southwest North America. So it is going to really matter what the future evolution of the tropical Pacific SSTs is. Looking at this now in the form of a time series, the historical one there is the 16-member ensemble, the shading forced by observed SSTs, and then the simulations continue out to 2040 with our scenarios. The ones at the top are the best case scenarios where the PDO goes positive, that's a warm tropical Pacific, and the AMO goes negative, so that's a cold North Atlantic. And that actually leads to some restoration of the amount of cool season precipitation. Whereas the worst case scenario is the Pacific remaining in its cool phase of the PDO and the Atlantic being in the warm phase of the tropical North Atlantic. The precipitation in that case continues to stay low. So, and the best case, the box and whiskers now show the best cases in terms of the variability plus the radiative forcing. So the very wettest cases, if we have the CMIP6 SST change, so the equatorial Pacific actually starts warming up, the positive phase of the PDO and the negative phase of the AMO. And in that case, we actually can have winter precipitation, cool season precipitation increasing. And that's in stark contrast to the worst case, which would be if the SST trends continue out into the future and we stay in a negative state of the PDO and the Atlantic goes into a warm phase of the AMO. In that case, we get cool season precipitation reducing. Both of these runs think that ensembles think that summer precipitation is actually going to reduce. So that's a radiatively forced reduction in summer precipitation. So for the worst case scenario where we reduce cool season precipitation, summer soil moisture is significantly below normal. But in the best case scenario, although cool season precipitation increased, it's actually a combination of enhanced evapotranspiration in the spring and reduced precipitation in the summer lead to the fact that the soil moisture actually hasn't really changed very much. So that's offsetting between cool season precip going up, ET going up, and then summer precip going down, allowing there to be little change. If we then look at the distribution across all ensemble members, so that's isolating the forced response for summer soil moisture, then we see that both in the CMIP6 case and the Hadley case, we're ending up with drier soils. The Hadley case, so that's the case of the observed SST extrapolated forward, is more robustly drier because of the classic La Nina-like teleconnection from the tropical Pacific. So it's more robustly drier than the case with the CMIP6. But even in that case where the equatorial Pacific is warming in CMIP6, we still have summer soil moisture decreasing. So just to finish up here now, this issue about summer soil moisture drying was first noticed long ago. There were several papers by this. I think Manabe, Weatherald, and Stouffer may have been the first to identify it in 1981, but there were similar papers at the time by Hansen and David Rind and others. And I've always sort of wondered, well, what is it that causes that? Is it reduced summer precipitation, or is it enhanced a warmer atmosphere holding more moisture such that the soils are being dried by enhanced evapotranspiration, or does it come about through some change earlier in the season? And I think it is often said, and you often see this said in the popular media, that yes, summer soil moisture goes down because the atmosphere can hold more moisture, and therefore it enhances evaporative demand, and evapotranspiration removes the water from the soil into the atmosphere. So in these runs, we decided to look at those dynamics much more closely. And we find instead that things are really being driven by the precipitation. So these are all scatter plots, 3 variable scatter plots for the next decade, like 2031 to 2041, minus the last 4 decades. So the last 4 spans the pluvial, then the Megadrought, and it's plotting all of the 84 ensemble members we have. So, you know, if you really want to scrutinize it, it's marked by the shape as to from which ensemble they came. But looking at the one on the top left, the thing that we notice is that as cool cool season precipitation declines, summer soil moisture declines. So that's the driving of summer soil moisture from the precipitation in the previous season. But we also see that the spring, as cool season precipitation declines, the spring evapotranspiration also declines. Or if precipitation increases in the winter, then spring evapotranspiration increases as well. So looked at that way, we're seeing that if there actually happens to be more precipitation in the winter, we quickly lose it to the atmosphere during enhanced spring evapotranspiration. So then moving over into the spring season, the plot on the top right is all spring conditions. And in this case, we see that as evapotranspiration increases in spring, the air humidity, the surface air humidity, also goes up, and the vapor pressure deficit actually declines. So in this case, this is clearly a relationship which is the soil evapotranspiration is the driver here. If we end up in a situation with more moisture from the winter, we can enhance spring evapotranspiration. That will then increase the air humidity, and the increased air humidity will make the vapor pressure deficit decline. So it's not the vapor pressure deficit driving the evapotranspiration. In this case, it's the other way round. And then moving down to the bottom left, where we're all within the summer, we see the case where summer soil moisture declines, the evapotranspiration also declines. So in that case, it's not the enhanced evapotranspiration that is driving the drier soils. It's drier soils leading to a reduction in evapotranspiration. And then that reduction in evapotranspiration leads to a reduction in precipitation, because in our model in summer, a significant amount of the summer precipitation is sourced from evapotranspiration from the soils. In fact, in some cases in the summer, the evapotranspiration can be declined by such that the net flux P minus ET is actually trying to restore the drying of the soils. It doesn't allow the soils to get wetter, but it's trying to reduce the amount of soil moisture drying. And then going around to the fall and the winter, in our model, there's a major reduction in fall precipitation across this region, and that's traceable to enhanced transient eddy moisture flux divergence, and that's occurring across all these ensembles, and that's reducing fall soil moisture. And then as fall soil moisture goes down, that causes the subsequent winter soil moisture to go down as well. So we're already drying soils in the summer, and then this fall radiatively forced reduction in precipitation related to enhanced transient eddy moisture divergence then allows further soil moisture drying, and then it connects round across the entire season. So in the interest of time, I will skip over this one, and which basically says the same thing in a form, and move to the conclusions so that we can have 10 minutes for a discussion. So there really is no scenario for the Southwest to return to late 20th century moisture availability. In the previous pictures where we saw the soil moisture appearing unchanged in the next decade relative to the last 4 decades, those last 4 decades combined the pluvial in 20th century and then the megadrought in the 21st century. So it's no change relative to that average, which means it's going to still be drier than the late 20th century pluvial. So those boom years, 1980s and 1990s for water, they're not coming back. The future summer soil moisture drought in the Southwest is very much precipitation controlled via these cross seasons, ocean, atmosphere, land connections. And then we can think about it. There's a best case. If the naturally occurring PDO swings positive, warms the tropical Pacific, and the AMO goes negative, which cools the tropical Atlantic, then we will have increased cool season precipitation. But that gets offset by enhanced evapotranspiration in the winter and spring, and it will not translate into an increase in summer soil moisture. Now, the worst case is that we remain or switch into a negative PDO with the cool tropical Pacific and the Atlantic goes warm. In that case, reduced cool season precipitation will reduce soil moisture year round. And then the evapotranspiration and air humidity decrease, which drives an actual increase in VPD. But the VPD here is responding to the precipitation-driven changes in soil moisture and evapotranspiration, not the other way around. So that's an opposite arrangement to the commonly said warming increases evaporative demand and dry soils. I've been guilty of saying that enough times as well, but I don't think that's in this area. I don't think that's what's happening here. And then the radiative forcing, which we get at by averaging across the full ensemble, that also drives a cool season precipitation decline. And it's more severe if strengthening of the zonal equatorial Pacific SST gradient continues out into the future. And since we think that that is an emerging pattern that's getting stronger over time, we think that for the next decade, 2-3 decades, we think it actually is going to strengthen. So we think that is the most likely scenario. So the forecast is continued megadrought. And that is where I will end. The picture here is just a reminder of what happened to another advanced civilization when they had to deal with a mega drought. Okay, thank you.
Thank you so much, Richard, for speaking today, and thank you all for attending our inaugural NOAA Drought Seminar Series. From Highland Wong at the NOAA National Weather Service Climate Prediction Center in Viva de Heza from the National Integrated Drought Information System, I'm Andy, and we thank you all for attending and hope to see you again next month.